Learning objectives. In this chapter, the user would learn the following in detail: multi-rate signal processing, adaptive signal processing, finite word length effect. Adaptive signal processing. Description of adaptive filtering operations at any time instant n. The reference noise V1 of n is processed by an adaptive filter with the time varying parameters W0 of n, W1 of n, etc. Wm-1 of n to produce the output signal. Y of n equal to summation k equal to 0 to m minus 1 Wk of n V1 of n minus k. The error signal is computed as E of n equal to D of n minus Y of n. The parameters of the filters are modified in an adaptive manner, for example, using the LMS algorithm, the simplest adaptive algorithm. Wk of n plus 1 equal to Wk of n plus mu V1 of n minus k into E of n, where mu is the adaptation constant. Rationale of the method. E of n equal to D of n minus Y of n equal to S of n plus V0 of n minus Y of n. E square of n equal to E s square of n plus E of V0 of n minus Y of n the whole square. E square of n depends on the parameters W0 of n, W1 of n, etc. Wm minus 1 of n. The algorithm in equation LMS modifies W0 of n, W1 of n, etc. Wm minus 1 of n such that E square of n is minimized. Since E square of n does not depend on the parameters Wk of n, the algorithm LMS minimizes E V0 of n minus Y of n the whole square. Thus, statistically, V0 of n will be close to Y of n, and therefore E of n approximately equal to S of n, within the bracket E of n will be close to S of n. Sketch of proof for equation LMS. E square of n equal to D of n minus Y of n the whole square equal to D of n minus W0 into V1 of n minus W1 into V1 of n minus 1 minus etc. Wm minus 1 into V1 of n minus m plus 1 the whole square. The square error surface E square of n equal to f of W0, etc. Wm minus 1 is a paraboloid. The gradient of square error is delta Wk E square of n equal to dE square of n divided by dWk equal to minus 2 into E of n into V1 of n minus k. The method of gradient descent minimization, Wk of n plus 1 equal to Wk of n minus mu into delta Wk E square of n equal to Wk of n plus mu into V1 of n minus k into E of n. Checking for effectiveness of equation LMS in reducing the errors. Epsilon n equal to D of n minus summation k equal to 0 to m minus 1 Wk of n plus 1 into V1 of n minus k equal to D of n minus summation k equal to 0 to m minus 1 Wk of n plus mu V1 of n minus k into E of n outside the bracket V1 of n minus k equal to D of n minus summation k equal to 0 to m minus 1 Wk of n into V1 of n minus k minus E of n into mu into summation k equal to 0 to m minus 1 V1 square of n minus k equal to E of n minus E of n into mu into summation k equal to 0 to m minus 1 V1 square of n minus k equal to E of n into within the bracket 1 minus mu into summation k equal to 0 to m minus 1 V1 square of n minus k. In order to reduce error by using the new parameters W of n plus 1, modulus of epsilon of n less than modulus of E of n, then 0 less than mu less than 2 divided by summation k equal to 0 to m minus 1 V1 square of n minus k. We can see in the figure adaptive noise cancelling. Applications using adaptive filters. We have to define who is the input signal into the filter U of t. What type of filter structure is used to compute Y of t? V is the desired ideal signal D of t against which we compare Y of t. Seldom the filter output Y of t is useful by itself. We may need only the parameters W of n or the error signal E of n. Identification, system identification, layered earth modeling, inverse modeling, predictive deconvolution, adaptive equalization. Prediction, linear predictive coding, ADPCM, autoregressive spectrum analysis, signal detection. Interference cancelling, adaptive noise cancelling, echo cancellation, radar polarimetry, adaptive beamforming. Example, adaptive noise cancelling, found in many applications, cancelling 50 Hz interference in electrocardiography, Widrow, 1975. Reduction of acoustic noise in speech, cockpit of a military aircraft, 10 to 15 dB reduction. Two measured inputs D of n and V1 of n. D of n comes from a primary sensor, D of n equal to S of n plus V0 of n, where S of n is the information bearing signal, V0 of n is the corrupting noise, V1 of n comes from a reference sensor. Hypothesis: the ideal signal S of n is not correlated with the noise sources V0 of n and V1 of n. Es of n into V0 of n minus k equal to 0, Vs of n into V1 of n minus k equal to 0 for all k. The reference noise V1 of n and the noise V0 of n are correlated with unknown cross correlation P of k. E V0 of n into V1 of n minus k equal to P of k. Noise cancellation with a fixed filter. Fixed filter noise cancelling, adaptive noise cancelling. Finite word length effects. Practical digital filters must be implemented with finite precision numbers and arithmetic. As a result, both the filter coefficients and the filter input and output signals are in discrete form. This leads to 4 types of finite word length effects. Discretization, quantization of the filter coefficient as the effect of perturbing the location of the filter poles and zeros. As a result, the actual filter response differs slightly from the ideal response. This deterministic frequency response error is referred to as coefficient quantization error. The use of finite precision arithmetic makes it necessary to quantize filter calculations by rounding or truncation. Round-off noise is the error in the filter output that results from rounding or truncating calculations within the filter. As the name implies, this error looks like low-level noise at the filter output. Quantization of the filter calculations also renders the filter slightly nonlinear. For large signals, this nonlinearity is negligible and round-off noise is the major concern. However, for recursive filters with a zero or constant input, this nonlinearity can cause spurious oscillations called limit cycles. With a fixed point arithmetic, it is possible for linear calculations to overflow. The term overflow oscillation, sometimes also called adder overflow limit cycle, refers to a high-level oscillation that can exist in an otherwise stable filter due to the non-linearity associated with the overflow of internal filter calculations. In this chapter, we examine each of these finite word length effects. Both fixed point and floating point number representations are considered. Number representation. In digital signal processing, B+1 bit fixed point numbers are usually represented as 2's complement signed fractions in the format B0, B-1, B-2, etc., B-B. The number represented is then x equal to minus B0 plus B-1 into 2 power minus 1 plus B-2 into 2 power minus 2 plus etc. plus B minus B into 2 power minus B is called equation number 10.3.1. where B0 is the sign bit and the number range is -1 less than or equal to x less than 1. The advantage of this representation is that the product of two numbers in the range from -1 to +1 is another number in the same range. Floating point numbers are represented as x equal to -1 whole power s into m into 2 power c is called equation number 10.3.2. where s is the sign bit, m is the mantissa and c is the characteristic or exponent. To make the representation of a number unique, the mantissa is normalized so that 0.5 less than or equal to m less than 1. Although floating point numbers are always represented in the form of 10.3.2, the way in which this representation is actually stored in a machine may differ. Since m greater than or equal to 0.5, it is not necessary to store the 2 minus 1 minus weight bit of m, which is always set. Therefore, in practice, numbers are usually stored as x equal to -1 whole power s 0.5 plus f into 2 power c is called equation number 10.3.3, where f is an unsigned fraction 0 less than or equal to f less than 0.5. Most floating point processors now use the IEEE standard 75432-bit floating point format for storing numbers. According to this standard, the exponent is stored as an unsigned integer p, where p equal to c plus 126 is called equation number 10.3.4. Therefore, a number is stored as x equal to -1 whole power s into 0.5 plus f into 2 power p minus 126 is called equation number 10.3.5. where s is the sign bit, f is a 23b unsigned fraction in the range 0 less than or equal to f less than 0.5, and p is an 8b unsigned integer in the range 0 less than or equal to p less than or equal to 255. The total number of bits is 1 plus 23 plus 8 equal to 32. For example, in IEEE format, 3 by 4 is written -1 whole power 0 into 0.5 plus 0.25 into 2 power 0. So, s equal to 0, p equal to 126 and f equal to 0.25. The value x equal to 0 is a unique case and is represented by all bits 0, that is s equal to 0, f equal to 0 and p equal to 0. Although the 2-1 weight mantissa bit is not actually stored, it does exist, so the mantissa has 24b plus a sign bit. Fixed point quantization errors. In fixed point arithmetic, a multiply doubles the number of significant bits. For example, the product of the two 5b numbers 0.0011 and 0.1001 is the 10b number 00.00011011. The extra bit to the left of the decimal point can be discarded without introducing any error. However, the least significant 4 of the remaining bits must ultimately be discarded by some form of quantization so that the result can be stored to 5b for use in other calculations. In the example above, this results in 0.0010 quantization by rounding or 0.0001 quantization by truncating. When a sum of products calculation is performed, the quantization can be performed either after each multiply or after all products have been summed with double length precision. We will examine 3 types of fixed point quantization: rounding, truncation, magnitude truncation. If x is an exact value, then the rounded value will be denoted QR of x, the truncated value QT of x, and the magnitude truncated value QMT of x. If the quantified value has b bits to the right of the decimal point, the quantization step sizes delta equal to 2 power minus b is called equation number 10.3.6. Since rounding selects the quantified value nearest to the unquantified value, it gives a value which is never more than plus or minus 1 by 2 away from the exact value. If we denote the rounding error by epsilon r equal to QR of x minus x is called equation number 10.3.7. Then minus delta by 2 less than or equal to epsilon r less than or equal to delta by 2 is called equation number 10.3.8. Truncation simply discards the low order bits, giving a quantified value always less than or equal to the exact value. So, minus delta less than epsilon t less than or equal to 0 is called equation number 10.3.9. Magnitude truncation chooses the nearest quantified value that has a magnitude less than or equal to the exact value. So, minus delta less than epsilon mt less than delta is called equation number 10.3.10. The error resulting from quantization can be modeled as a random variable uniformly distributed over the appropriate error range. Therefore, calculations with round off error can be considered error-free calculations that have been corrupted by additive white noise. The mean of this noise for rounding is m epsilon r equal to E of epsilon r equal to 1 by delta integral minus delta by 2 to delta by 2 epsilon r d epsilon r equal to 0 is called equation number 10.3.11, where E of bracket represents the operation of taking the expected value of a random variable. Similarly, the variance of the noise for rounding is sigma epsilon r square equal to expectation of epsilon r minus m epsilon r the whole square equal to 1 by delta integral minus delta by 2 to delta by 2 epsilon r minus m epsilon r the whole square into d epsilon r equal to del square by 12 is called equation number 10.3.12. Likewise, for truncation, m epsilon t equal to E of epsilon t equal to minus delta by 2 sigma epsilon t square equal to E of epsilon t minus m epsilon t the whole square equal to del square by 12 is called equation number 10.3.13. And for magnitude truncation, m epsilon mt equal to E of epsilon mt equal to 0 sigma epsilon mt square equal to E of epsilon mt minus m epsilon mt the whole square equal to delta square by 3 is called equation number 10.3.14. Floating point quantization errors. With floating point arithmetic, it is necessary to quantize after both multiplications and additions. The addition quantization arises because prior to addition, the mantissa of the smaller number in the sum is shifted right until the exponent of both numbers is the same. In general, this gives a sum mantissa that is too long and so must be quantized. We will assume that quantization in floating point arithmetic is performed by rounding. Because of the exponent in floating point arithmetic, it is the relative error that is important. The relative error is defined as epsilon r equal to q r of x minus x divided by x equal to epsilon r by x is called equation number 10.3.15. Since x equal to minus 1 whole power s into m into 2 power c into q r of x equal to minus 1 whole power s into q r of m into 2 power c, and epsilon r equal to q r of m minus m divided by m equal to epsilon by m is called equation number 10.3.16. If the quantified mantissa has b bits to the right of the decimal point, modulus less than 1 by 2, whereas before 1 equal to 2 minus b. Therefore, since 0.5 less than or equal to m less than 1, modulus of epsilon r less than delta is called equation number 10.3.17. If we assume that is uniformly distributed over the range from minus 1 by 2 to 1 by 2 and m is uniformly distributed over 0.5 to 1, m epsilon r equal to E of epsilon by m equal to 0, sigma epsilon r square equal to E of epsilon by m the whole square equal to 2 by delta integral 1 by 2 to 1, again integral minus delta by 2 to delta by 2 epsilon square by m square d epsilon into dm equal to del square by 6 equal to 0.167 into 2 power minus 2b is called equation number 10.3.18. In practice, the distribution of m is not exactly uniform. Actual measurements of round off noise in 1 suggested that sigma epsilon r square equal to 0.23 delta square is called equation number 10.3.19, while a detailed theoretical and experimental analysis in 2 determined sigma epsilon r square approximately equal to 0.18 delta square is called equation number 10.3.20. from 10.3.15, we can represent a quantized floating point value in terms of the unquantized value and the random variable epsilon r using qr of x equal to x of 1 plus epsilon r is called equation number 10.3.21. Therefore, the finite precision product x1, x2 and the sum of x1, x2 can be written f L of x1, x2 equal to x1, x2 of 1 plus epsilon r is called equation number 10.3.22, and FL of x1 plus x2 equal to x1 plus x2 into 1 plus epsilon r is called equation number 10.3.23, where epsilon r is 0 mean with the variance of 10.3.20. Round of noise. To determine the round of noise at the output of a digital filter, we will assume that the noise due to a quantization is stationary, white and uncorrelated with the filtered input, output and internal variables. This assumption is good if the filter input changes from sample to sample in a sufficiently complex manner. It is not valid for zero or constant inputs, for which the effects of rounding are analyzed from a limit cycle perspective. To satisfy the assumption of a sufficiently complex input, round of noise in digital filters is often calculated for the case of a zero mean white noise filter input signal x of n of variance sigma square of x. This simplifies calculation of the output round of noise because expected values of the form E of x of n into x of n minus k are 0 for k not equal to 0 and give sigma square x when k equal to 0. This approach to analysis has been found to give estimates of the output round of noise that are close to the noise actually observed for other input signals. Another assumption that will be made in calculating round of noise is that the product of two quantization errors is 0. To justify this assumption, consider the case of a 16B fixed point processor. In this case, a quantization error is of the order 215, while the product of two quantization errors is of the order 230, which is negligible. If a linear system with impulse response g of n is excited by white noise with mean mx and variance sigma square x, the output is noise of mean. My equal to mx summation n equal to minus infinity to plus infinity g of n is called equation number 10.3.24, and variance sigma y square equal to sigma x square into summation n equal to minus infinity to plus infinity g square of n is called equation number 10.3.25. Therefore, if g of n is the impulse response from the point where a round off takes place to the filter output, the contribution of that round off to the variance mean square value of the output round of noise is given by 10.3.25 with the sigma square x replaced with the variance of the round off. If there is more than one source of round off error in the filter, it is assumed that the errors are uncorrelated, so the output noise variance is simply the sum of the contributions from each source. Round off noise in FIR filters. The simplest case to analyze is a finite impulse response FIR filter realized via the convolution summation y of n equal to summation k equal to 0 to n minus 1 h of k into x of n minus k is called equation number 10.3.26. When fixed point arithmetic is used and quantization is performed, after each multiply, the result of the n multiples is n times the quantization noise of a single multiply. For example, rounding after each multiply gives from 10.3.6 and 10.3.1 to an output noise variance of sigma naught square equal to n into 2 power minus 2b by 12 is called equation number 10.3.27. Virtually all digital signal processor integrated circuits contain one or more double length accumulator registers which permit the sum of products in 10.3.26 to be accumulated without quantization. In this case, only a single quantization is necessary following the summation, and sigma naught square equal to 2 power minus 2b by 12 is called equation number 10.3.28. For the floating point round of noise case, we will consider 10.3.26 for n equal to 4 and then generalize the result to other values of n. The finite precision output can be written as the exact output plus an error term E of n, then y of n plus c of n equal to h of 0 into x of n into 1 plus epsilon 1 of n plus h of 1 into x of n minus 1 into 1 plus epsilon 2 of n into 1 plus epsilon 3 of n plus h of 2 into x of n minus 2 into 1 plus epsilon 4 of n into 1 plus epsilon 5 of n plus h of 3 into x of n minus 3 plus epsilon 6 of n into 1 plus epsilon 7 of n is called equation number 10.3.29. In 10.3.29, epsilon 1 of n represents the error in the first product, epsilon 2 of n the error in the second product, epsilon 3 of n the error in the first addition, etc. Notice that it has been assumed that the products are summed in the order implied by the summation of 10.3.26. Expanding 10.3.29, ignoring products of error terms and recognizing y of n gives E of n equal to h of 0 into x of n into epsilon 1 of n plus epsilon 3 of n plus epsilon 5 of n plus epsilon 7 of n plus h of 1 into x of n minus 1 epsilon 2 of n plus epsilon 3 of n plus epsilon 5 of n plus epsilon 7 of n plus h of 2 into x of n minus 2 into epsilon 4 of n plus epsilon 5 of n plus epsilon 7 of n plus h of 3 x of n minus 3 into epsilon 6 of n plus epsilon 7 of n is called equation number 10.3.30. Assuming that the input is white noise of variance sigma square x, so that E of x of n into x of n minus k is 0 for k is not equal to 0, and assuming that the errors are uncorrelated. E of e square of n equal to 4h square of 0 plus 4h square of 1 plus 3h square of 2 plus 2h square of 3 sigma x square into sigma epsilon r square is called equation number 10.3.31. In general, for any n, sigma naught square equal to E of e square of n equal to n h square of 0 plus summation k equal to 1 to n minus 1 n plus 1 minus k into h square of k sigma x square into sigma epsilon r square is called equation number 10.3.32. Notice that if the order of summation of the product terms in the convolution summation is changed, then the order in which the h of k's appear in 10.3.32 changes. If the order is changed so that the h of k with the smallest magnitude is first, followed by the next smallest, etc., then the round of noise variance is minimized. However, performing the convolution summation in non-sequential order greatly complicates data indexing and so may not be worth the reduction obtained in round of noise. Round of noise in fixed point IIR filters. To determine the round of noise of a fixed point infinite impulse response IIR filter realization, consider a causal first order filter with impulse response h of n equal to a power n into u of n is called equation number 10.3.33, realized by the difference equation y of n equal to a into y of n minus 1 plus x of n is called equation number 10.3.34. Due to round of error, the output actually obtained is y cap of n equal to q of a y of n minus 1 plus x of n equal to a y of n minus 1 plus x of n plus e of n is called equation number 10.3.35. Where e of n is a random round of noise sequence, since e of n is injected at the same point as the input it propagates through a system with impulse response h of n. Therefore, for fixed point arithmetic with rounding, the output round of noise variance from 10.3.6, 10.3.12, 10.3.25 and 10.3.33 is sigma naught square equal to del square by 12 into summation n equal to minus infinity to plus infinity h square of n equal to del square by 12 into summation n equal to 0 to infinity a power 2n equal to 2 power minus 2b divided by 12 into 1 divided by 1 minus a square is called equation number 10.3.36. With fixed point arithmetic, there is the possibility of overflow following addition. To avoid overflow, it is necessary to restrict the input signal amplitude. This can be accomplished by either placing a scaling multiplier at the filter input or by simply limiting the maximum input signal amplitude. Consider the case of the first order filter of 10.3.34. The transfer function of this filter is h of e power j omega equal to y of e power j omega divided by x of e power j omega equal to 1 divided by e power j omega minus a is called equation number 10.3.37. So, modulus of h of e power j omega the whole square equal to 1 divided by 1 plus a square minus 2a cos omega is called equation number 10.3.38. And modulus of h of e power j omega maximum equal to 1 divided by 1 minus a is called equation number 10.3.39. The peak gain of the filter is 1 divided by 1 minus modulus of a. So, limiting input signal amplitudes to modulus of x of n less than or equal to 1 minus modulus of a will make overflow unlikely. An expression for the output round of noise to signal ratio can easily be obtained for the case where the filter input is white noise uniformly distributed over the interval from minus of 1 minus modulus of a to 1 minus modulus of a in closed interval 4, 5. In this case, sigma x square equal to 1 divided by 2 into 1 minus modulus of a integral minus of 1 minus modulus of a to 1 minus modulus of a x square into dx equal to 1 by 3 into 1 minus modulus of a the whole square is called equation number 10.3.40. So, from 10.3.25, sigma y square equal to 1 by 3 into 1 minus modulus of a the whole square divided by 1 minus a square is called equation number 10.3.41. Comparing 10.3.36 and 10.3.41 gives sigma naught square divided by sigma y square equal to 2 power minus 2b divided by 12 into 1 by 1 minus a square into 3 into 1 minus a square divided by 1 minus modulus of a the whole square equal to 2 power minus 2b divided by 12 into 3 divided by 1 minus modulus of a the whole square is called equation number 10.3.42. Notice that the noise to signal ratio increases without bound as modulus of a minus 1. Similar results can be obtained for the case of the causal sound order filter realized by the difference equation y of n equal to 2r cos theta y of n minus 1 minus r square y of n minus 2 plus x of n is called equation number 10.3.43. This filter has complex conjugate poles at or e power plus or minus j theta and impulse response h of n equal to 1 by sine of theta into r power n into sine of n plus 1 of theta into u of n is called equation number 10.3.44. Due to round off error, the output actually obtained is y cap of n equal to 2r cos theta y of n minus 1 minus r square y of n minus 2 plus x of n plus e of n is called equation number 10.3.45. Therefore, two noise sources contributing to e of n if quantization is performed after each multiply, and that is one noise source if quantization is performed after summation. Since summation n equal to minus infinity to plus infinity, h square of n equal to 1 plus r square divided by 1 minus r square into 1 divided by 1 plus r square the whole square minus 4 r square into cos square theta is called equation number 10.3.46. The output round of noise is sigma naught square equal to v into 2 minus 2b divided by 12 into 1 plus r square by 1 minus r square into 1 by 1 plus r square the whole square minus 4 r square cos square theta is called equation number 10.3.47, where v equal to 1 for quantization after summation and v equal to 2 for quantization after each multiply. To obtain an output noise to signal ratio, we note that h of e power j omega equal to 1 divided by 1 minus 2r cos theta into e power minus j omega plus r square e power minus j 2 omega is called equation number 10.3.48, and using the approach modulus of h of e power j omega the whole square maximum equal to 1 divided by 4r square of that of 1 plus r square by 2r cos theta minus 1 plus r square by 2r cos theta the whole square plus 1 minus r square by 2r sin theta the whole square is called equation number 10.3.49, where sat of mu equal to 1 for mu less than 1, mu for minus 1 less than or equal to mu less than or equal to 1, minus 1 for mu less than minus 1 is called equation number 10.3.50. Following the same approach as for the first order case then gives sigma naught square by sigma y square equal to v into 2 power minus 2b divided by 12 into 1 plus r square by 1 minus r square into 3 divided by 1 plus r square the whole square minus 4r square cos square theta into 1 divided by 4r square into sat of 1 plus r square by 2r cos theta minus 1 plus r square by 2r cos theta the whole square plus 1 minus r square by 2r sin theta the whole square is called equation number 10.3.51. Normalized fixed point round off noise variation. Round off noise in floating point IIR filters. For floating point arithmetic, it is first necessary to determine the injected noise variance of each quantization. For the first order filter, this is done by writing the corrupted output as y of n plus e of n equal to a y of n minus 1 into 1 plus epsilon 1 of n plus x of n 1 plus epsilon 2 of n is called equation number 10.3.52, where epsilon 1 of n represents the error due to the multiplication and epsilon 2 of n represents the error due to the addition. Neglecting the product of errors, 10.3.52 becomes y of n plus e of n approximately equal to a y of n minus 1 plus x of n plus a y of n minus 1 into epsilon 1 of n plus a y of n minus 1 into epsilon 2 plus x of n into epsilon 2 of n is called equation number 10.3.53. Comparing 10.3.34 and 10.3.53, it is clear that e of n equal to a y of n minus 1 into epsilon 1 plus a y of n minus 1 into epsilon 2 of n plus x of n into epsilon 2 of n is called equation number 10.3.54. Taking the expected value of E2 of n to obtain the injected noise variance then gives E of E square of n equal to a square into E of y square of n minus 1 into E of epsilon 1 square of n plus a square into E of y square of n minus 1 plus E of epsilon 2 square of n plus E of x square of n into E of epsilon 2 square of n plus E of x of n into y of n minus 1 into E of epsilon 2 square of n is called equation number 10.3.55. To carry this further, it is necessary to know something about the input. If we assume the input is 0 mean white noise with variance sigma x square, then E x square of n equal to sigma x square, and the input is uncorrelated with past values of the output. So E of x of n into y of n minus 1 equal to 0, giving E of E square of n equal to 2a square sigma y square sigma epsilon r square plus sigma x square sigma epsilon r square is called equation number 10.3.56, and sigma naught square equal to 2a square into sigma y square into sigma epsilon r square plus sigma x square into sigma epsilon r square into summation n equal to minus infinity to plus infinity h square of n equal to 2a square into sigma y square plus sigma x square divided by 1 minus a square into sigma epsilon r square is called equation number 10.3.57. However, sigma y square equal to sigma x square into summation n equal to minus infinity to plus infinity h square of n equal to sigma x square divided by 1 minus a square is called equation number 10.3.58. So, sigma naught square equal to 1 plus a square divided by 1 minus a square the whole square into sigma epsilon r square into sigma x square equal to 1 plus a square divided by 1 minus a square into sigma epsilon r square into sigma y square is called equation number 10.3.59. And the output round off noise to signal ratio is sigma naught square divided by sigma y square equal to 1 plus a square divided by 1 minus a square into sigma epsilon r square is called equation number 10.3.60. Similar results can be obtained for the second order filter of 10.3.43 by writing y of n plus e of n equal to 2r cos theta y of n minus 1 into 1 plus epsilon 1 of n minus r square y of n minus 2 1 plus epsilon 2 of n into 1 plus epsilon 3 of n plus x of n into 1 plus epsilon 4 of n is called equation number 10.3.61. Expanding with the same assumptions as before gives e of n approximately equal to 2r cos theta into y of n minus 1 into epsilon 1 of n plus epsilon 3 of n plus epsilon 4 of n minus r square y of n minus 2 epsilon 2 of n plus epsilon 3 of n plus epsilon 4 of n plus x of n into epsilon 4 of n is called equation number 10.3.62. And e of e square of n equal to 4r square cos square theta sigma y square plus 3 sigma epsilon r square plus r square sigma y square into 3 sigma epsilon r square plus sigma x square into sigma epsilon r square minus 8r cube into cos theta into sigma epsilon r square into e of y of n minus 1 into y of n minus 2 is called equation number 10.3.63. However, e of y of n minus 1 into y of n minus 2 equal to e of 2r cos theta into y of n minus 2 minus r square y of n minus 3 plus x of n minus 1 into y of n minus 2 equal to 2r cos theta into e of y square n of n minus 2 minus r square into e of y of n minus 2 into y of n minus 3 equal to 2r cos theta e of y square of n minus 2 minus r square into e of y of n minus 1 into y of n minus 2 equal to 2r cos theta divided by 1 plus r square into sigma y square is called equation number 10.3.64. So, e of e square of n equal to sigma epsilon r square into sigma x square plus within the bracket 3r power 4 plus 12r square cos square theta minus 16r power 4 cos square theta divided by 1 plus r square outside the bracket sigma epsilon r square into sigma y square is called equation number 10.3.65. And sigma naught square equal to e of e square of n into summation n equal to minus infinity to plus infinity h square of n equal to epsilon into within the bracket sigma epsilon r square into sigma x square plus within the bracket 3r square plus 12r square cos square theta minus 16r power 4 cos square theta divided by 1 plus r square outside the bracket sigma epsilon r square into sigma y square is called equation number 10.3.66. Where from 10.3.46 epsilon equal to summation n equal to minus infinity to plus infinity h square of n equal to 1 plus r square divided by 1 minus r square into 1 divided by 1 plus r square the whole square minus 4r square into cos square theta is called equation number 10.3.67. Since sigma y square equal to epsilon into sigma x square, the output round off noise to signal ratio is then sigma naught square divided by sigma y square equal to epsilon into within the bracket 1 plus epsilon into within the bracket 3r power 4 plus 12r square into cos square theta minus 16r power 4 into cos square theta divided by 1 plus r square outside the bracket sigma epsilon r square is called equation number 10.3.68. Normalized floating point round off noise variance. Limit cycles. A limit cycle, sometimes referred to as a multiplier round off limit cycle, is a low level oscillation that can exist in an otherwise stable filter as a result of the non-linearity associated with rounding or truncating internal filter calculations. Limit cycles require recursion to exist and do not occur in non-recursive FIR filters. As an example of a limit cycle, consider the second order filter realized by y of n equal to QR of 7 by 8 into y of n minus 1 minus 5 by 8 into y of n minus 2 plus x of n is called equation number 10.3.69. Where QR represents quantization by rounding. This is stable filter with poles at 0.4375 plus or minus j into 0.6585. Consider the implementation of this filter with 4b, 3b and a sign bit. To complement fixed point arithmetic, 0 initial conditions y of minus 1 equal to y of minus 2 equal to 0 and an input sequence x of n equal to 3, 8 delta of n, where delta of n is the unit impulse or unit sample. The following sequence is obtained: y of 0 equal to qr of 3 by 8 equal to 3 by 8. Similarly, we can write y of 1, y of 2, etc. y of 12 is called equation number 10.3.70. Notice that while the input is 0 except for the first sample, the output oscillates with amplitude 1 by 8 and period 6. Limit cycles are primarily of concern in fixed point recursive filters. As long as floating point filters are realized as the parallel or cascade connection of first and second order subfilters, limit cycles will generally not be a problem, since limit cycles are practically not observable in first and second order systems implemented with 32B floating point arithmetic. It has been shown that such systems must have an extremely small margin of stability for limit cycles to exist at anything other than underflow levels, which are at an amplitude of less than 1038. There are at least 3 ways of dealing with limit cycles when fixed point arithmetic is used. One is to determine a bound on the maximum limit cycle amplitude expressed as an integral number of quantization steps. It is then possible to choose a word length that makes the limit cycle amplitude acceptably low. Alternately, limit cycles can be prevented by randomly rounding calculations up or down. However, this approach is complicated to implement. The third approach is to properly choose the filter realization structure and then quantize the filter calculations using magnitude truncation. This approach has the disadvantage of producing more round of noise than truncation or rounding. Overflow oscillations. With fixed point arithmetic, it is possible for filter calculations to overflow. This happens when two numbers of the same sign add to give a value having magnitude greater than 1. Since numbers with magnitude greater than 1 are not representable, the result overflows. For example, the two complement numbers 0.101 5 by 8 and 0.1004 by 8 add to give 1.001, which is the 2's complement representation of -7 by 8. The overflow characteristic of 2's complement arithmetic can be represented as R, where R of x equal to x minus 2 for x greater than or equal to 1, x for minus 1 less than or equal to x less than 1, x plus 2 for x less than minus 1 is called equation number 10.3.71. For the example, just consider R of 9 by 8 equal to minus 7 by 8. An overflow oscillation, sometimes also referred to as an adder overflow limit cycle, is a high-level oscillation that can exist in an otherwise stable fixed point filter due to the gross non-linearity associated with the overflow of internal filter calculations. Like limit cycles, overflow oscillations require recursion to exist and do not occur in non-recursive FIR filters. Overflow oscillations also do not occur with floating point arithmetic due to the virtual impossibility of overflow. As an example of an overflow oscillation, once again consider the filter of 10.3.69 with the 4 minus b fixed point 2's complement arithmetic and with the 2's complement overflow characteristic of 10.3.71. Y of n equal to q r of 7 by 8 y of n minus 1 minus 5 by 8 y of n minus 2 plus x of n is called equation number 10.3.72. In this case, we apply the input x of n equal to minus 3 by 4 delta of n minus 5 by 8 delta of n minus 1 equal to minus 3 by 4 minus 5 by 8 comma 0 comma 0 etc. is called equation number 10.3.73. Giving the output sequence: y of 0 equal to qr of r of minus 3 by 4 equal to qr of minus 3 by 4 equal to minus 3 by 4. Similarly, we can write y of 1, y of 2 etc. y of 8 is called equation number 10.3.74. This is a large scale oscillation with a nearly full scale amplitude. There are several ways to prevent overflow oscillations in fixed point filter realizations, the most obvious is to scale the filter calculation so as to render overflow impossible. However, this may unacceptably restrict the filter dynamic range. Another method is to forced completed sums of products to saturate at plus or minus 1 rather than overflowing. It is important to saturate only the completed sum, since intermediate overflows in 2's complement arithmetic do not affect the accuracy of the final result. Most fixed point digital signal processors provide for automatic saturation of completed sums if their saturation arithmetic feature is enabled. Yet another way to avoid overflow oscillations is to use a filter structure for which any internal filter transient is guaranteed to decay to zero. Such structures are desirable anyway, since they tend to have low round of noise and be insensitive to coefficient quantization. Coefficient quantization error. Each filter structure has its own finite, generally non-uniform grids of realizable pole and zero locations. When the filter coefficients are quantized to a finite word length, in general, the pole and zero locations desired in filter do not correspond exactly to the realizable locations. The error in filter performance usually measured in terms of a frequency response error resulting from the placement of the poles and zeros at the non-ideal but realizable locations is referred to as coefficient quantization error. Consider the second order filter with complex conjugate poles lambda equal to r into e power plus or minus j theta equal to lambda r plus or minus j lambda I equal to r cos theta plus or minus j r sin theta is called equation number 10.3.75. And a transfer function h of z equal to 1 divided by 1 minus 2r cos theta into z power minus 1 plus r square into z power minus 2 is called equation number 10.3.76. Realized by the difference equation y of n equal to 2r cos theta into y of n minus 1 minus r square into y of n minus 2 plus x of n is called equation number 10.3.77. The grid is defined by the intersection of vertical lines corresponding to quantization of 2 lambda r and concentric circles corresponding to quantization of minus r square. Realizable pole locations for the difference equation of 10.3.76. The sparseness of realizable pole locations near z equal to plus or minus 1 will result in a large coefficient quantization error for poles in this region. Figure gives an alternative structure to 10.3.77 for realizing the transfer function of 10.3.76. Notice that quantizing the coefficients of the structure corresponds to quantizing lambda r and lambda I. This results in a uniform grid of realizable pole locations. Therefore, large coefficient quantization errors are avoided for all pole locations. It is well established that filter structures with low round of noise tend to be robust to coefficient quantization and vice versa. For this reason, the uniform grid structure is also popular because of its low round of noise. Likewise, the low noise realization of can be expected to be relatively insensitive to coefficient quantization, and digital wave filters and lattice filters that are derived from low sensitivity analog structures tend to have not only low coefficient sensitivity but also low round of noise. It is well known that in a high order polynomial with clustered roots, the root location is a very sensitive function of the polynomial coefficients. Therefore, filter poles and zeros can be much more accurately controlled if higher order filters are realized by breaking them up into the parallel or cascade connection of first and second order subfilters. One exception to this rule is the case of linear phase FIR filters, in which the symmetry of the polynomial coefficients and the spacing of the filter zeros around the unit circle usually permits an acceptable direct realization using the convolution summation. Given a filter structure, it is necessary to assign the ideal pole and zero locations to the realizable locations. This is generally done by simply rounding or truncating the filter coefficients to the available number of bits, or by assigning the ideal pole and zero locations to the nearest realizable locations. A more complicated alternative is to consider the original filter design problem as a problem in discrete optimization and choose the realizable pole and zero locations that give the best approximation to the desired filter response. Alternate realization structure. Realizable pole locations from the alternate realization structure. Realization considerations. Linear phase FER digital filters can generally be implemented with acceptable coefficient quantization sensitivity using the direct convolution sum method. When implemented in this way, on a digital signal processor, fixed point arithmetic is not only acceptable but may actually be preferable to floating point arithmetic. Virtually all fixed point digital signal processors accumulate a sum of products in a double length accumulator. This means that only a single quantization is necessary to compute an output. Floating point arithmetic, on the other hand, requires a quantization after every multiply and after every add in the convolution summation. With 32B floating point arithmetic, these quantizations introduce a small enough error to be insignificant for many applications. When realizing IIR filters, either a parallel or cascade connection of first and second orders of filters is almost always preferable to a high order direct form realization. With the availability of very low cost floating point digital signal processor like the Texas Instruments TMS320C32, it is highly recommended that floating point arithmetic be used for IIR filters. Floating point arithmetic simultaneously eliminates most concerns regarding scaling, limit cycles, and overflow oscillations. Regardless of the arithmetic employed, a low round of noise structure should be used for the second order sections. The use of a low round of noise structure for the second order sections also tends to give a realization with low coefficient quantization sensitivity. First order sections are not as critical in determining the round of noise and coefficient sensitivity of a realization, and so can generally be implemented with a simple direct form structure. Multi-rate signal processing. A key feature of the discrete time systems discussed so far is that the signals at the input, output, and every internal node have the same sampling rate. However, there are many practical applications that either require or can be implemented more efficiently by processing signals at different sampling rates. Discrete time systems with different sampling rates at various parts of the systems are called multi-rate systems. The practical implementation of multi-rate systems requires changing the sampling rate of a signal using discrete time operations, that is, without reconstructing and resampling a continuous time signal. The fundamental operations for changing the sampling rate are decimation and interpolation. The subject of this chapter is the analysis, design, and efficient implementation of decimation and interpolation systems and their application of two important areas of multi-rate signal processing: sampling rate conversion and multi-rate filter banks. Study objectives: understand the operations of decimation, interpolation, and arbitrary sampling rate change in the time and frequency domains. Understand the efficient implementation of discrete time systems for sampling rate conversion using polyphase structures. Design a special type of filter, Nyquist filters, which are widely used for the efficient implementation of multi-rate filters and filter banks. Understand the operation, properties, and design of two-channel filter banks with perfect reconstruction analysis and synthesis capabilities. Sampling rate conversion. The sampling rate conversion process can be regarded as a two-step operation. First, the discrete time signal is reconstructed into a continuous time signal, then it is resampled at a different sampling rate. Given a discrete time signal x of n, we can determine a continuous time signal xc of t such that x of n equal to xc of nt by using the band limited interpolation. Xc of t equal to summation k equal to minus infinity to plus infinity x of n into sin pi of t minus nt divided by t divided by pi of t minus nt divided by t is called equation number 10.1.1. Because of the way it was formed, the signal xc of t as Fourier transform xc of j ohm equal to 0 for modulus of ohm greater than pi by t. Furthermore, the spectra of x of n and xc of t are related by x of e power j ohm t equal to 1 by t summation k equal to minus infinity to plus infinity xc of j of omega minus k omega s is called equation number 10.1.12, where omega s equal to 2 pi divided by t is the sampling frequency. Sampling rate decreased by an integer factor. Suppose that we sample a continuous time signal xc of t with the sampling periods t and td, where d is an integer. The corresponding discrete time signals x of n equal to xc of nt and xd of n equal to xc of ntd are related by xd of n approximately equal to dd of x of n approximately equal to x of nd approximately equal to x into compressed d of n is called equation number 10.1.3. The system defined by 10.1.3 is called a downsampler or sampling rate compressor SRC or simply compressor because it reduces the sampling rate of a discrete time signal downsampling by an integer factor d. The system is essentially a discrete time sampler which retains only one out of each group of d consecutive input samples into its output. The compressor can be implemented in MATLAB by the function y equal to src of x comma d, y equal to x of 1 is to d is to length of x is called equation number 10.1.4. We note that the samples of x of n for n not equal to md are lost in the downsampling. The MATLAB SP tool provides a function y equal to downsample x comma d comma k is called equation number 10.1.5. To implement the operation y of n equal to x of nd plus k, where k equal to 0, 1, etc. up to d minus 1, the spectrum of the sampled discrete time signal x d of m is given by x d of e power j omega td equal to 1 divided by td summation L equal to minus infinity to plus infinity xc of j into omega minus L omega d equal to 1 divided by dt summation L equal to minus infinity to plus infinity xc of j into omega minus L into 2 pi divided by dt is called equation number 10.1.6, where omega d equal to 2 pi divided by td equal to omega s divided by d is the reduced sampling rate. Figure block diagram representation of sampling rate compressor system. We can see in the figure sampling rate compressor. The spectrum x d of e power j omega td of the decimated sequence can be obtained directly by putting replicas of the spectrum x of e power j omega t of the original sequence at omega equal to m of omega s divided by d for m equal to 0, 1, etc. up to d minus 1. Adding them and then scaling the sum of 1 by d, this result can be obtained analytically by expressing the summation index in 10.1.16 as follows. L equal to m plus kd, where 0 less than or equal to m less than or equal to d minus 1 is called equation number 10.1.7. Basically, this indexing breaks the infinite summation with index into a sum of d infinite summations with index k. Indeed, replacing by m plus kd yields x d of e power j omega td equal to 1 by d summation m equal to 0 to d minus 1 by t into summation k equal to minus infinity to plus infinity x e of j of omega minus m into 2 pi by dt minus k into 2 pi by t is called equation number 10.1.8. Comparing the term within the square brackets to 10.1.2, we obtain 1 by t into summation k equal to minus infinity to plus infinity x c of j of omega minus m into 2 pi by dt minus k into 2 pi by t equal to x of e power j of omega minus 2 pi m divided by dt into t is called equation number 10.1.9. Substituting 10.1.9 into 10.1.8 and using d equal to 2 pi divided by td, we obtain the desired result x d of e power j omega td equal to 1 by d summation m equal to 0 to d minus 1 x of e power j of omega minus m omega d into t is called equation number 10.1.10. If we define the normalized frequency variable as omega approximately equal to omega td is called equation number 10.1.11, and note that omega t equal to omega td divided by d equal to omega divided by d. We can express 10.1.10 as follows: x d of e power j omega equal to 1 by d summation m equal to 0 to d minus 1 x of e power j of omega minus 2 pi m divided by d. Figure: frequency domain illustration of sampling rate reduction. We now turn our attention to the graphical construction of x d of e power j omega directly from x of e power j omega. This process involves the following steps. Number 1. Stretch x of e power j omega by a factor d to obtain x of e power j omega by d. We note that the highest frequency omega h is repositioned to frequency omega equal to omega hd. Number 2. Create and put d copies of x of e power j omega by d at the frequencies omega equal to 2 pi m integer multiples of 2 pi for m equal to 0, 1, etc. d minus 1. Number 3. Add the d stretched and shifted replicas and then divide by d to obtain the spectrum x d of e power j omega of the downsampled sequence x d of n equal to x of nd. Figure: frequency domain interpretation of downsampling for d equal to 3. To establish a closure analogy between continuous time and discrete time sampling, we define the discrete time sampling rate fs approximately equal to 1 by d or omega s equal to 2 pi by d is called equation number 10.1.13, which simply means keep 1 out of every d samples. Then the condition that should be satisfied to avoid aliasing can be stated as: if x of e power j omega equal to 0, omega h less than or equal to modulus of omega less than or equal to pi, then omega s equal to 2 pi by d greater than or equal to 2 omega h is called equation number 10.1.14, or equivalently fs equal to 1 by d greater than or equal to 2 times of fh or omega h equal to 2 pi fh. Figure: representation of a system for sampling rate decreased by an integer factor d. The combined system is called a decimator and the corresponding process is known as decimation. If we use an FIR low pass filter of order m, the output of the decimator is x d of m equal to v of md equal to summation k equal to 0 to m h of k into x of md minus k is called equation number 10.1.15. Since only every dth output of the filter is needed the overall computational cost is reduced by a factor of d. The samples of the input signal are shifted in memory every t seconds, but the filter computes the output only every t by d seconds. That is, the filter computes one output sample every d input samples. See tutorial problem 1. The fundamental difference between 10.1.15 and convolution is that the input sequence or equivalently the impulse response is shifted by d samples instead of one sample when the output sequence index changes by 1. MATLAB also provides two functions to perform decimation. The first one defined by MATLAB functions for decimation. Y equal to FIRDN of x, h, 1, d is called equation number 10.1.16. Provides the same functionally as is given in 10.1.15. The second function y equal to decimate of x, d, m, FIR is called equation number 10.1.17. Designs and uses an math order low pass FIR filter with cutoff frequency omega c equal to n by d using function FIR1. Figure A. Downsampling d equal to 2 with aliasing. B. Downsampling with low pass pre-filtering decimation to avoid aliasing. The distortion caused by low pass filtering is less damaging than aliasing distortion. Figure MATLAB function for implementation of an FIR decimator. The continuous time signal x omega t can be perfectly reconstructed from the samples x d of m using the ideal band limited interpolation formula. X c of t equal to summation m equal to minus infinity to plus infinity x d of m into sin pi of t minus m dt divided by pi of t minus m dt divided by dt is called equation number 10.18. If we evaluate 10.1.18 at t equal to nt and recall that x of n equal to x c of nt, we obtain x of n equal to summation n equal to minus infinity to plus infinity x d of n into sin pi of n minus md divided by pi of n minus md divided by d is called equation number 10.1.19, which provides perfect reconstruction of x of n directly from x d of m. Clearly, the ideal discrete time interpolator 10.1.19 is not practically realizable. However, practical approximations obtained by windowing the ideal interpolation sequence and using the DFT are possible. Sampling rate increased by an integer factor. Increasing the sampling rate of a discrete time signal x of n by an integer factor I, unsampling requires the insertion of I minus 1 samples between consecutive samples of x of n. Upsampling is an information preserving operation. If we consider the underlying continuous time signal xc of t, the ideal goal is to obtain a sequence of samples x1 of n approximately equal to xc of nt1 equal to xc of nt divided by L is called equation number 10.1.20, where ti equal to t divided by I. From the samples of the discrete time signal x of n equal to xc of nt is called equation number 10.1.21. This can be done using the interpolation formula 10.1.19, simply replacing d by I. Thus, the interpolated signal xi of n is obtained using the formula x1 of n equal to summation m equal to minus infinity to plus infinity x of m into sin pi of n minus mi divided by pi of n minus mi divided by I is called equation number 10.1.22. the ideal interpolation kernel in 10.1.22 and its Fourier transform are given by GB1 of n approximately equal to sin pi n by I divided by pi n by I tends to GB1 of e power j omega equal to I for 0 less than or equal to modulus of omega less than or equal to pi divided by I, and 0 for pi by L less than modulus of omega less than or equal to pi is called equation number 10.1.23. In general, the interpolation process is described by the formula x1 of n equal to summation n equal to minus infinity to plus infinity x of m into gt of n minus ml is called equation number 10.1.24, which yields the ideal interpolator 10.1.22 if gr of n equal to gbl of n. Since gbl of 0 equal to 1, gbl of ni equal to 0 for n equal to 0, the ideal interpolator does not alter the original samples. Thus, we usually require gr of n to have the following property: gr of n equal to 1 for n equal to 0, 0 for n equal to plus or minus I, plus or minus 2i, etc. is called equation number 10.1.25. To understand the operation described by 10.1.24, we evaluate the Fourier transform of the interpolated sequence xi of n. The result is given by xi of e power j omega equal to summation m equal to minus infinity to plus infinity x of m into gr of e power j omega into e power minus j mi omega is called equation number 10.1.26a equal to gr of e power j omega into summation m equal to minus infinity to plus infinity x of m into e power minus j mi omega is called equation number 10.1.26b. Since the spectrum of the original sequence x of n is given by x of e power j omega equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n is called equation number 10.1.27. We can express relation 10.1.26b as x1 of e power j omega equal to gr of e power j omega into x of e power j omega l is called equation number 10.1.28. We note that for I equal to 1, the operation specified by 10.1.24 is a convolution sum. In this case, formula 10.1.28 is the frequency domain description of an LTI system. To understand the meaning of 10.1.28 for I not equal to 1, we explicitly write x of e power j omega I as follows: x of e power j omega I equal to summation m equal to minus infinity to plus infinity x of m into e power minus j omega I m equal to etc. plus x of 0 plus x of 1 into e power minus j I omega plus x of 2 into e power minus j 2i omega plus etc. is called equation number 10.1.29. Therefore, if we define a sequence x u of n by inserting I minus 1 zeros between consecutive samples of x of n, that is by x u of n approximately equal to u1 of x of n approximately equal to x compressed to x of n approximately equal to x of n by I, n is a multiple of I and 0 otherwise, is called equation number 10.1.30. We have in the frequency domain x u of e power j omega equal to x of e power j omega I is called equation number 10.1.31. The system described by 10.1.30 is called upsampler or sampling rate expander SRE. The SRE is implemented in MATLAB by the function y equal to SRE x, I, y equal to zeros of 1 is to I star length of x, y of 1 is to I is to length of y equal to x. MATLAB provides the more general function y equal to upsample of x comma I comma k, which expands the input by a factor of I and then shifts the obtained sequence by inserting k zeros, where k equal to 0, 1, etc. I minus 1 in the beginning. Figure representation of a sampling rate expander. We can now use the SRE to obtain an alternative implementation of the interpolation operation. Indeed, substitution of 10.1.31 into 10.1.28 gives x1 of e power j omega equal to gr of e power j omega into xu of e power j omega is called equation number 10.1.32, which corresponds to an LTI system described by the convolution summation x1 of n equal to summation k equal to minus infinity to plus infinity xu of k gr of n minus k is called equation number 10.1.33. A general system for increasing the sampling rate by an integer factor I can be implemented by a SRE followed by a filter with impulse response gr of n. The sequence gr of n used in 10.1.24 and 10.1.33 are identical. However, the interpretation is different. In the former case, gr of n is the kernel or characteristic sequence of a linear time varying interpolation system. In the later case, gr of n is the impulse response of a low pass filter. Figure discrete time system for sampling rate increased by an integer factor I using ideal band limited interpolation. Frequency domain interpretation. To understand the interpolation process in the frequency domain, we start with the upsampler since xu of e power plus or minus j pi equal to x of e power plus or minus j pi I. We conclude that I periods of e power j omega are compressed and form one period of xu of e power j omega. The extra I minus 1 copies of the compressed spectrum introduced by upsampling are called images. The upsampler creates an imaging effect. The interpolation filter GBI of e power j omega removes all these images and scales the spectrum by I to compensate for the 1 by I reduction in signal bandwidth. If the interpolation filter has a cutoff frequency larger than pi by I, or we use a non-ideal filter, energy from the images remains in the interpolated signal. This type of distortion is known as post-aliasing in the computer graphics literature. We note that increasing the sampling period by an integer factor d inserts d minus 1 replicas xc of j in the original Nyquist range and then reduces its width by a factor d. The SRE increases the Nyquist range by a factor I by including d minus 1 additional copies of xc of j. If we use the normalized time index n equal to t by t, downsampling increases the rate of change of the output signal. However, because we use the normalized frequency variable omega equal to t, the width of the Nyquist range is always equal to 2 pi. Therefore, downsampling stretches the input signal spectrum by a factor d and upsampling compresses the input spectrum by a factor I. This is essentially a consequence of the scaling theorem for the discrete time Fourier transform. Figure frequency domain interpretation of interpolation for I equal to 3. MATLAB functions for interpolation. There are two MATLAB functions that can be used to interpolate a sequence x of n by a factor I. The function y equal to interpolation of x comma I uses an internally designed low-pass filter. The function y equal to up FIR dn of x comma h comma I comma 1 uses an FIR filter provided by the user. Figure: decimation and interpolation operations in the time and frequency domains for d equal to I equal to 2 using the physical time t and the physical frequency omega variables. Figure: decimation and interpolation operations in the time and frequency domains for d equal to I equal to 2 using the normalized time n and the normalized frequency omega variables. Sampling rate change by a non-integer factor. The interpolator increases the sampling rate by a factor I and the decimator decreases the sampling rate by a factor d. The effective sampling rate of the output signal is t0 equal to 1 by t into I by d. Because decimation may cause aliasing, we always put the interpolator first to preserve the spectrum of x of n. Since the interpolation and decimation low-pass filters are in cascade and operate at the same sampling rate, they can be replaced by a single low-pass filter. This filter is defined by h of e power j omega equal to 1 for 0 less than or equal to modulus of omega less than or equal to minimum of pi by I comma pi by d and 0 minimum of pi by I comma pi by d less than or equal to modulus of omega less than or equal to pi, where I greater than d. Sampling rate increase, the common filter acts as an anti-imaging post filter to remove the images introduced by the upsampling operation, where I less than d. Sampling rate decrease. The common filter acts as an anti-aliasing filter for the downsampling operation if the original signal is not properly band limited. Thus, with the proper choice of I and D, we can approximate any desired ratio of sampling periods to any degree of accuracy. This approach is practical when I and D are small integers. When the ratio I by D involves large values, for example 511 divided by 255 or T0 divided by T is not a ratio of integers, it may be preferable to use techniques developed to change the sampling rate by arbitrary factors. Figure A. System for changing the sampling rate by a rational factor. B. Simplified system obtained by combining interpolation and decimation filters. Implementation of multi-rate systems. In this section, we discuss the structures for efficient implementation of sampling rate conversion by a rational factor. The derived structures, besides their widespread applicability in multi-rate signal processing applications, have some interesting theoretical properties and find use in other areas of signal processing. Sampling rate compressors and expanders. Since sampling rate compressors and expanders are linear but time varying, they do not have a system function h of z equal to y of z given x of z. However, we can express y of z as a function that involves some form of x of z. Sampling rate compressor. We use a two-step process. We first sample x of n by multiplying with the periodic sampling train. Delta of d of n equal to summation k equal to minus infinity to plus infinity, delta of n minus kd equal to 1 by d, summation k equal to 0 to d minus 1, w d power minus kn, where wd approximately equal to expectation of minus j 2 pi by d. The z transform of the sampled sequence. V of n approximately equal to x of n into delta d of n is determined by the following steps. V of z equal to summation k equal to minus infinity to plus infinity, x of n into delta d of n into z power minus n equal to summation k equal to minus infinity to plus infinity, x of n into 1 by d into summation k equal to 0 to d minus 1, w d power minus k into z power minus n equal to 1 by d into summation k equal to 0 to d minus 1 into summation k equal to minus infinity to plus infinity x of n into wk d power z whole power minus n equal to 1 by d into summation k equal to 0 to d minus 1 x of wk dz. Since y of n equal to v of nd equal to x of nd, the z transform of y of n can be expressed as y of z equal to summation n equal to minus infinity to plus infinity v of nd into z power minus n equal to summation m equal to minus infinity to plus infinity v of m into z power 1 by d the whole power minus m equal to v of z power 1 by d. Combining above equations, we obtain the desired relation y of n equal to x of nd under z y of z equal to 1 by d summation k equal to 0 to d minus 1 x of wk dz power 1 by d. Sampling rate expander. The sampling rate expander was defined by y of n equal to x of n by I, where n equal to 0, plus or minus I, plus or minus 2i, etc. is called equation number 10.1.34. The z transform of the output is given by y of z equal to summation n equal to minus infinity to plus infinity x of n by I into z power minus n equal to summation m equal to minus infinity to plus infinity x of m into z power minus im is called equation number 10.1.35, which implies that y of z equal to x of z power I is called equation number 10.1.36. Figure. Multi-rate identities. Two equivalent systems A and B for downsampling and two equivalent systems C and D for upsampling. It is possible to interchange the filter with a compressor or expander if we properly modify the filter. The multi-rate identities. We next derive two identities known as multi-rate identities, which are widely used to understand and simplify the operation of multi-rate systems. Interchange of filtering with downsampling. The output of the system in figure A is described by y of z equal to h of z into v1 of z equal to h of z into 1 by d into summation k equal to 0 to d minus 1 x of z power 1 by d into w d power k is called equation number 10.1.37. y of z equal to 1 by d into summation k equal to 0 to d minus 1 v2 of z power 1 by d into w d power k equal to h of z into 1 by d into summation k equal to 0 to d minus 1 x of z power 1 by d into w d power k is called equation number 10.1.38 because v2 of z equal to h of z power d into x of z equal to w d power kd equal to 1. From 10.1.37 and 10.1.38 we conclude that the two systems are equivalent. Thus we can interchange the order of downsampling and filtering if we upsample the impulse response of the filter. Interchange of filtering with upsampling. The output of the system in figure C is given by y of z equal to v1 of z power I equal to h of z power I into x of z power I is called equation number 10.1.39. The output of the system in figure D is y of z equal to h of z power I into v2 of z equal to h of z power I into x of z power I is called equation number 10.1.40. Comparison of 10.1.39 and 10.1.40 shows that the two structures are equivalent. Thus, we can interchange the order of filtering and upsampling if we upsample the impulse response of the filter. Polyphase filter structures. Polyphase filter structures are widely used to simplify implementation of decimators and interpolators. Consider an FIR filter with length n equal to ml. The polyphase decomposition breaks the impulse response into m subsequence of length L. The basic idea is best illustrated by means of a simple example. For n equal to 6 and m equal to 2, we group together even and odd terms as follows. H of z equal to h of 0 plus h of 1 into z power minus 1 plus h of 2 into z power minus 2 plus h of 3 into z power minus 3 plus h of 4 into z power minus 4 plus h of z into z power minus 5 equal to h of 0 plus h of 2 into z power minus 2 plus h of 4 into z power minus 4 plus z power minus 1 into h of 1 plus h of 3 into z power minus 2 plus h of 5 into z power minus 4 is called equation number 10.1.41. If we define following subfilters, P0 of z approximately equal to h of 0 plus h of 2 into z power minus 1 plus h of 4 into z power minus 2 is called equation number 10.1.42a. P1 of z approximately equal to h of 1 plus h of 3 into z power minus 1 plus h of 5 into z power minus 2 is called equation number 10.1.42b. We can express h of z as follows. H of z equal to P0 of z square plus z power minus 1 into P1 of z square is called equation number 10.1.43. For m equal to 3, we obtain the following decomposition. H of z equal to P naught of z cube plus z power minus 1 into P1 of z cube plus z power minus 2 into P2 of z cube is called equation number 10.1.44, where the polyphase components are given by P naught of z approximately equal to h of 0 plus h of 3 into z power minus 1 is called 10.1.45a. P1 of z approximately equal to h of 1 plus h of 4 into z power minus 1 is called equation number 10.45b. P2 of z approximately equal to h of 2 plus h of 5 into z power minus 1 is called equation number 10.1.45c. We note that when n, the length of the impulse response, is a composite number, there are multiple polyphase decompositions. In general, the impulse response of the kth subfilter is obtained by downsampling the shifted sequence h of n plus k by a factor m, that is pk of n approximately equal to h of nm plus k, where k equal to 0, 1, etc. up to m minus 1 is called equation number 10.1.46. Therefore, we have h of z equal to summation k equal to 0 to m minus 1 z power minus k into pk of z power m is called equation number 10.1.47, where pk of z equal to summation n equal to 0 to l minus 1 pk of n into z power minus n is called equation number 10.1.48. In MATLAB, the polyphase decomposition can easily be obtained using the reshape function, assuming that n, the length of h of n, is a multiple of m. We have p equal to reshape of h comma m comma length of h by m is called equation number 10.1.49. If n is not a multiple of m, we append h of n with the proper number of zeros. The zeros of the matrix P contain the polyphase components of the impulse response. Using 10.1.44 for m equal to 3, we note that the z transform of the output sequence y of n can be expressed into two equivalent forms as follows. Y of z equal to h of z into x of z equal to p naught of z cube into x of z plus z power minus 1 into p1 of z cube into x of z plus z power minus 2 into p2 of z cube into x of z is called equation number 10.1.50a equal to p naught of z cube into x of z plus z power minus 1 into p1 of z cube into x of z plus z power minus 1 into p2 of z cube into x of z is called equation number 10.1.50b. Polyphase structures for decimation and interpolation. The most important application of polyphase structures is in implementation of computationally efficient decimators and interpolators. Figure A, realization of the direct form polyphase structure, and B, the transposed form polyphase structure. Both structures are shown for m equal to 3. Figure decimation system. Let us express the filter h of z using the polyphase structure 10.1.47, 10.1.48, with m equal to d, the result is as follows. H of z equal to summation k equal to 0 to m minus 1 h of k into z power minus k equal to summation k equal to 0 to d minus 1 pk of z into z power minus k is called equation number 10.1.51a. pk of z equal to summation n equal to 0 to l minus 1 pk of n into z power minus n is called equation number 10.1.51b. pk of n equal to h of nd plus k, where k equal to 0, 1, etc. up to d minus 1 is called equation number 10.1.51c, where we have assumed that m equal to ld, otherwise we paired h of n with zeros. Applying the multi-rate identity for downsampling to the system leads to the structure. The output of the polyphase decimator is y of n equal to summation k equal to 0 to d minus 1, yk of n equal to summation k equal to 0 to d minus 1, pk of n star xk of n is called equation number 10.1.52, where the inputs to the parallel bank of polyphase filters are given by xk of n equal to x of nd minus k, where k equal to 0, 1, etc. d minus 1 is called equation number 10.1.53, or more explicitly x naught of n equal to x of 0, x of d, x of 2d, x of 4d, etc. x1 of n equal to 0, x of d minus 1, x of 2d minus 1, x of 4d minus 1, etc. x of d minus 1 of n equal to 0, x of 1, x of d plus 1, x of 2d plus 1, etc. Figure: polyphase implementation of a decimation system before applying the downsampling identity A and after applying the downsampling identity B. The output of each polyphase filter is given by pk of n equal to h of ni plus k, where k equal to 0, 1, etc. up to I minus 1 is called 10.1.54a. yk of n equal to pk of n star x of n is called equation number 10.1.54b. y of m equal to yk of n into m equal to nl plus k is called equation number 10.1.54c. The upsampling and delay operations can be replaced by the commutator structure. We note that while the filtering operation takes place at the lower input sampling rate, the commutator picks up sequentially samples from the MATLAB implementation of a polyphase FIR decimator. Figure: polyphase decimator with a commutator instead of delays. Figure: interpolation system. Figure: polyphase interpolation structure before A and after B. The application of the multi-rate identity for upsampling. Figure: polyphase interpolator with a commutator instead of delays. Figure: MATLAB implementation of a polyphase FIR interpolator. MATLAB functions for rational rate conversion. The MATLAB SP toolbox provides two functions for rational sampling rate conversion. The function y equal to resample of x, I, d resamples the signal in array x at I by d times the original sampling rate to obtain y. The resulting resampled array y as the length given by tail I by d star length of x. The function resample also has additional input and output parameters for which the SP toolbox manual should be consulted. The second function y equal to up FIR dn of x, h, I, d performs a rational rate conversion using three operations. It first upsamples the input signal array x by the factor I, then performs FIR filtering on the upsampled signal using the impulse response in H, and finally downsamples the result by a factor d to obtain the resampled signal in array y. Filter design for multi-rate systems. The ideal low-pass filters required for practical sampling rate conversion are usually approximated by FIR filters designed. In this section, we discuss some special filters that are particularly useful in multi-rate systems. However, these filters also have uses in other applications. Off-band and kth band Nyquist FIR filters. Decimation and interpolation by a factor of 2 require low-pass filters with cutoff frequency omega c equal to pi by 2. That is ideal off-band filters. The impulse response of this ideal filter is h of n equal to omega c by pi into sine omega c of n minus alpha divided by omega c of n minus alpha at omega c equal to pi by 2 equal to 1 by 2 for n equal to a, 0 for n minus alpha equal to plus or minus 2, plus or minus 4, etc. is called equation number 10.1.55. To simplify the discussion, we assume alpha equal to 0, that is, we consider non-causal zero phase filters with the real frequency response h of e power j omega. In this case, we have h of 0 equal to 1 by 2, h of 2n equal to 0, n equal to plus or minus 1, plus or minus 2, etc. is called equation number 10.1.56. Thus, the polyphase representation of 10.1.51a is given by h of z equal to p naught of z square plus z power minus 1 into p1 of z square equal to 1 by 2 plus z power minus 1 into p1 of z square is called equation number 10.1.57, where p naught of z equal to summation n h of 2n into z power minus n and p1 of z equal to summation n h of 2n plus 1 into z power minus n. In general, any filter with h of minus n equal to h of n or h of e power minus j omega equal to h of e power j omega that satisfies 10.1.56 is called a off-band filter. Using 10.1.57, we can easily derive the property h of z plus h of minus z equal to 1 is called 10.1.58. Evaluating this relationship on the unit circle yields h of e power j omega plus h of e power j of omega minus pi equal to 1 is called equation number 10.1.59. If we change the variable omega to pi by 2 plus theta, we obtain the following relation: h of e power j of pi by 2 plus theta minus 1 by 2 equal to minus h of e power j pi by 2 minus theta minus 1 by 2 is called equation number 10.1.60. First, we note that the m by 2 zeros in the impulse response reduce the amount of computations by almost 1/2. Second, we note h of e power j omega has odd symmetry about omega equal to plus or minus pi by 2. The implications of this symmetry for a practical low pass filter are: a. The peak error delta 1 and delta 2 are equal, and b. The band edges omega p and omega s are symmetric with respect to pi by 2. Hence, we have delta p equal to delta s is called 10.1.61a. Omega p equal to pi minus omega s is called 10.1.61b. Figure: impulse response and frequency response of a off-band FIR filter with order m equal to 18. Notice the odd symmetry of h of e power j omega about omega equal to plus or minus pi by 2. The kth band or Nyquist filter, which is a natural extension of the off-band filter, is defined as a zero phase FIR whose impulse response satisfies the condition h of n equal to 1 by k for n equal to 0, 0 for n equal to plus or minus k, plus or minus 2k, etc. is called equation number 10.1.62. The impulse response of the ideal kth band filter is given by 10.1.55 with omega c equal to pi by k. The polyphase decomposition of a Nyquist filter is given by the generalization of 10.1.57. H of z equal to 1 by k plus summation k equal to 1 to k minus 1 z power minus k into pk of z power k is called 10.1.63, and similarly 10.1.58 can be generalized to summation k equal to 0 to k minus 1 h of z into w k power k equal to 1 is called equation number 10.1.64, where wk equal to e power minus j 2 pi by k. If we set z equal to e power j omega, we obtain relation summation k equal to 0 to k minus 1 h of e power j of omega minus 2 pi k by k equal to 1 is called equation number 10.1.65. Thus, the sum of k copies of the frequency response of a Nyquist filter shifted successively by 2 pi by k rats is equal to unity. An efficient approach to the design of equiripple off-band filters is using the Park-McClellan algorithm. This approach consists of the following steps. Number 1. Given the specifications omega s, ap and as of the off-band filter, obtain the parameters delta p, delta s and omega p so that they satisfy the design requirements and the constraint of the off-band filter, that is delta approximately equal to minimum of delta p comma delta s, omega p equal to pi minus omega s is called equation number 10.1.65. Number 2. Design a single band type 2 FIR filter g of z of order m by 2 equal to 2p minus 1 odd with omega p equal to 2 omega p, omega s equal to pi and delta equal to 2 delta using the Parks-McClellan algorithm. Since g of z is type 2, the frequency response g of e power j omega is equal to 0 at omega equal to pi. Number 3. Scale the impulse response g of n by 1 of upsample the result by a factor of 2 and set the middle coefficient to 1 by 2. The result is an impulse response h of n with system function h of z given by h of z equal to 1 by 2 into z power minus m by 2 plus g of z square is called equation number 10.1.66, which is a off-band filter with the pass-band cutoff frequency omega p. Multi-stage decimation and interpolation. Decimation by an integer factor d requires an FIR filter with cutoff frequency omega c equal to pi by d. For large d, the passband of the filter becomes very narrow, which requires an even smaller transition band delta omega. Since for FIR filters the order m increases with 1 by delta omega, large decimation factors require long FIR filters with very short transition bands. Such filters are difficult to design and require a large number of computations. An efficient way to avoid these problems is to use a multi-stage approach. To this end, consider the two-stage decimation system where the overall decimation factor is d equal to d1 into d2. We note that the cutoff frequency omega c equal to pi by d for a single stage decimator is much smaller than the cutoff frequencies omega power 1 c equal to pi by d1 of h1 of z or omega power 2 c equal to pi by d1 of h2 of z. Therefore, the filters h1 of z and h2 of z are easier to design and have shorter lengths if we interchange the order of downsampler by d1 with the low pass filter h2 of z using the multirate identity for downsampling. We obtain the system combining the two filters and the two downsamplers yields the equivalent single stage decimation system. The equivalent single stage decimator has a factor D equal to D1 into D2 and a low pass filter with the system function h of z equal to h1 of z into h2 of z power d is called equation number 10.1.67. Figure A to C. Conversion of a two-stage decimation system to an equivalent one-stage system using the multirate identity for downsampling. Interpolated FIR/IFIR filters. To understand the principle of IFIR filters, consider a prototype low-pass filter f of z with cutoff frequency omega c. If we replace z by z power l, we obtain a filter FL of z equal to f of z power l such that FL of n equal to f of n, where n equal to 0, plus or minus l, plus or minus 2l, etc. and 0 otherwise. Under DTFT, it gives FL of e power j omega equal to f of e power j omega l. We note that FL of n is obtained by upsampling f of n by a factor l, and FL of e power j omega is constructed by squeezing l periods of f of e power j omega between 0 and 2 pi. A similar process was used to create COM filters. The frequency response FL of e power j omega contains L minus 1 compressed images of f of e power j omega. The system function of the combined filter is given by h of z equal to f of z power l into g of z. This process is equivalent to interpolation of the impulse response f of n using the interpolator. This interpretation is responsible for the term interpolated FIR filter. Conversion of a two-stage interpolation system to an equivalent one-stage system using the multirate identity for upsampling. Two-channel filter banks. A filter bank is a collection of filters with a common input or a common output. There are two basic types of filter bank. Number 1. The analysis filter bank splits a signal x of n into k signals vk of n, known as subband signals, using the analysis filters hk of z. Number 2. The synthesis filter bank consists of k synthesis filters gk of z, which combine k signals sk of n into a signal y of n. If sk of n equal to vk of n, for k equal to 0, 1, etc. up to k minus 1, we would like y of n to provide an accurate reconstruction of x of n. A problem with the analysis filter bank is that the number of output samples is k times the number of input samples. Analysis and synthesis filter banks for k equal to 3 channels. In most applications, the subband signals are obtained by dividing the spectrum into k separate bands using filters with overlapping bands to prevent gaps in the spectrum. If all subbands have the same width, the filter bank is called uniform, and however, in certain applications, it may be preferable to use non-uniform filter banks. Thus, filter banks use low pass, band pass and high pass filters to cover the entire frequency range. Frequency response of a low pass prototype and the resulting uniform DFT filter bank for k equal to 6 due to periodicity. The filter h naught of e power j omega covers the two ends of the fundamental frequency range. This processed subband signals should be interpolated by a factor of k before they are combined to form the output signal. These ideas lead to the maximally decimated multirate filter bank. A maximally decimated multirate filter bank with k equal to 3 channels. Input-output description. Consider the two-channel filter bank using delta d of n equal to summation k equal to minus infinity to plus infinity delta of n minus kd equal to 1 by d summation k equal to 0 to d minus 1 w d power minus kn and y of z equal to summation n equal to minus infinity to plus infinity v of nd into z power minus n equal to summation m equal to minus infinity to plus infinity v of m into z power 1 by d the whole power minus m equal to v of z power 1 by d. The output of the upper channel is described by the following equations. V naught of z equal to 1 by 2 into h naught of z power 1 by 2 into x of z power 1 by 2 plus 1 by 2 into h naught of minus z power 1 by 2 into x of minus z power 1 by 2. Y naught of z equal to V naught of z square into G naught of z. Y naught of z equal to 1 by 2 into within the bracket h naught of z into x of z plus h naught of minus z into x of minus z outside the bracket G naught of z. In a similar way, the output of the lower channel is y1 of z equal to 1 by 2 into within the bracket h1 of z into x of z plus h1 of minus z into x of minus z outside the bracket g1 of z. The output y of n equal to y naught of n plus y1 of n of the synthesis filter bank is given by y of z equal to 1 by 2 into t of z into x of z plus a of z into x of minus z, where t of z approximately equal to h naught of z into g naught of z plus h1 of z into g1 of z. A of z approximately equal to h naught of minus z into g naught of z plus h1 of minus z into g1 of z. Two channel filter bank. Explanation of the alias generation and cancellation mechanism in the frequency domain for B, the low pass channel, and C, the high pass channel. Conditions for perfect reconstruction. The condition for perfect or distortionless reconstruction is y of n equal to gx of n minus nd under z, y of z equal to gz power minus nd into x of z is called equation number 10.1.74. The perfect reconstruction is possible if and only if a of z equal to h naught of minus z into g naught of z plus h1 of minus z into g1 of z equal to 0 is called equation number 10.1.75a. T of z equal to h naught of z into g naught of z plus h1 of z into g1 of z equal to gz power minus nd is called equation number 10.1.75b, which can be written in matrix form as follows, is called equation number 10.1.76. The condition 10.1.75a ensures the elimination of aliasing distortion from the output signal. The condition 10.1.75b, which requires T of Z to be all-pass filter with a linear phase, guarantees the absence of amplitude and phase distortion from the reconstructed signal. We set G equal to 2 to preserve the amplitude of the output signal. If we have determined the analysis filters, we can obtain the synthesis filters by solving the linear system of equations. The result is g naught of z equal to 2 into z power minus nd divided by delta m of z into h1 of minus z, g1 of z equal to minus 2 into z power minus nd divided by delta m of z into h naught of minus z is called equation number 10.1.77, where delta m of z, the determinant of the matrix in 10.1.76, is given by delta m of z equal to h naught of z into h1 of minus z minus h naught of minus z into h1 of z is called equation number 10.1.78. The solutions in 10.1.77 exist if delta m of z not equal to 0. We note that choosing the synthesis filters according to 10.1.77 ensures cancellation of aliasing error for any choice of analysis filters. Then the condition 10.1.75b for perfect reconstruction becomes z power nd into h naught of z into g naught of z plus z power nd into h1 of z into g1 of z equal to 2 is called equation number 10.1.78. To facilitate the analysis and design process, we define a product filter R of z by R of z approximately equal to z power nd h naught of z into g naught of z is called equation number 10.1.79. Inserting g naught of z from 10.1.76 into 10.1.79, the product filter can be written in terms of the analysis filters as R of z equal to 2 divided by delta m of z into h naught of z into h1 of minus z is called equation number 10.1.80. Since delta m of minus z equal to minus delta m of z, we can express the product z power nd into h1 of z into g1 of z as z power nd into h1 of z into g1 of z equal to minus 2 divided by delta m of z into h naught of minus z into h1 of z equal to r of minus z is called equation number 10.1.81. The last two expressions make it possible to express the perfect reconstruction condition 10.1.78 in terms of a single product filter R of z using the relation R of z plus R of minus z equal to 2 is called equation number 10.1.82. The product filter R of z plays a crucial role in analyzing and designing filter banks. Perfect reconstruction condition 10.1.82 imposes some critical constraints on the structure of R of z. Indeed, using the following polyphase decomposition of R of z. R of z equal to R naught of z square plus z power minus 1 into R1 of z square is called equation number 10.1.83. The perfect reconstruction condition 10.1.82 yields R naught of z square plus z power minus 1 into R1 of z square plus R naught of z square minus z power minus 1 into R1 of z square equal to 2 is called equation number 10.1.84, which implies that R naught of z square equal to 1. Therefore, the product filter in 10.1.83 is given by R of z equal to 1 plus z power minus 1 into R1 of z square is called equation number 10.1.85. In conclusion, to design a two-channel perfect reconstruction filter bank, it is necessary and sufficient to obtain an R of z satisfying 10.1.84. Perform the factorization R of z equal to z power nd into h naught of z into g naught of z and assign the remaining filters from 10.1.77. The choice of R of z and the particular factorization taken determine the properties of the filter bank. There are two cases of primary interest. Number 1, the product filter R of z equal to h of z into h z power minus 1 is the z transform of an autocorrelation sequence. This requires the design of a single filter and leads to what is known as orthogonal or para-unitary filter banks. Number 2, the product filter R of z equal to h naught of z into g naught of z is the z transform of a correlation sequence. This requires the design of two filters and leads to the more general bi-orthogonal filter banks. Perfect reconstruction orthogonal FIR filter banks. From 10.1.77 and 10.1.78, we conclude that in general, the synthesis filters G naught of Z and G1 of Z will be IIR, even if the analysis filters H naught of Z and H1 of Z are FIR. However, if H naught of Z and H1 of Z are FIR filters and the determinant satisfies the condition delta M of Z equal to C naught into Z power minus N naught is called equation number 10.1.86. The synthesis filters obtained by 10.1.77 will be FIR as well. The first FIR filter bank with perfect reconstruction was introduced independently by Smith and Banwell 1984 and Minster 1985. They defined the analysis filters in terms of a single mth order FIR prototype filter H of Z as H naught of Z equal to H of Z is called equation number 10.1.87a. H1 of Z equal to minus Z power minus M into H of minus Z power minus 1 is called equation number 10.1.87b. Filters satisfying 10.1.87 are called conjugate quadrature filters, CQFs, if we assume that the order M of the prototype filter H of Z is odd. The determinant becomes delta M of Z equal to H naught of Z into H1 of minus Z minus H naught of minus Z into H1 of Z equal to Z power minus M of H of Z into H of Z power minus 1 plus H of minus Z into H of minus Z power minus 1 is called equation number 10.1.88. To ensure that the synthesis filters are also FIR, we require that H of Z into H of Z power minus 1 plus h of minus z into h of minus z power minus 1 equal to 1 is called equation number 10.1.89. Since h of z has real coefficients, we have h of e power minus j omega equal to h of e power j omega. Thus evaluating 10.1.89 on the unit circle yields the equivalent frequency domain condition. Modulus of h of e power j omega the whole square plus modulus of h of e power j of omega minus pi the whole square equal to 1 is called equation number 10.1.90. Using 10.1.97, we can also express 10.1.90 as follows. Modulus of h naught of e power j omega the whole square plus modulus of h1 of e power j omega the whole square equal to 1 is called equation number 10.1.91. Two filters h naught of z and h1 of z that satisfy the condition 10.1.91 are called power complementary. This term is also used for any filters that satisfy 10.1.89 or 10.1.90. Comparing 10.1.88 with 10.1.86, we conclude that when 10.1.87 holds C0 equal to 1 and N0 equal to M, if we also choose ND equal to M, the synthesis filters are given by G0 of Z equal to 2 times of H1 of minus Z equal to minus 2 times of Z power minus M into H of Z power minus 1 is called equation number 10.1.92a. G1 of Z equal to minus 2 times of H0 of minus Z equal to minus 2 into H of minus Z is called equation number 10.1.92b. To check whether the filter bank specified by 10.1.88 and 10.1.92 as a perfect reconstruction property, we note that the product filter is given by R of Z equal to Z power ND, H0 of Z into G0 of Z equal to 2 times of H of Z into H of Z power minus 1 is called equation number 10.1.93. Therefore, the perfect reconstruction condition becomes R of Z plus R of minus Z equal to 2 times of H of Z into H of Z power minus 1 plus 2 times of H of minus Z into minus Z power minus 1 equal to 2 is called equation number 10.1.94, which is identical to 10.1.89. Thus, if the filter bank defined by 10.1.87 and 10.1.92 satisfies the condition 10.1.89, it has the perfect reconstruction property. Equivalently, we conclude that the product filter R of Z is a off-band filter. In addition, we need to know under what conditions a filter H of Z that satisfies 10.1.89 exists, that is, when the solution of the spectral factorization problem 10.1.93 exists, or H of Z equal to H of Z into H of Z power minus 1 is called equation number 10.1.95 is equal to the autocorrelation sequence of H of n, that is, we have or H of n equal to H of n star H of minus n under Z, or H of Z equal to H of Z into H of Z power minus 1 is called equation number 10.1.96. Since H of n is real, the Fourier transform of 10.1.96 is given by or H of e power j omega equal to modulus of H of e power j omega the whole square greater than or equal to 0 is called equation number 10.1.97. This condition guarantees the solution of the spectral factorization problem 10.1.93. Thus, a filter H of Z satisfying 10.1.89 exists if the product filter 10.1.93 satisfies the condition R of e power j omega greater than or equal to 0. Since the autocorrelation sequence 10.1.96 is equal to 0 for even n except n equal to 0, using 10.1.96 we obtain summation k equal to 0 to m h of k into h of k plus 2n equal to 0 for n not equal to 0 is called equation number 10.1.98. If we normalize h of n to have unit energy, that is, summation n equal to 0 to m modulus of h of n the whole square equal to 1 is called equation number 10.1.99. We can express the perfect reconstruction requirement in the time domain as summation k equal to 0 to m h of k into h of k plus 2n equal to delta of n is called equation number 10.1.100. Note that for m equal to 3 we have h of z equal to h of 0 plus h of 1 into z power minus 1 plus h of 2 into z power minus 2 plus h of 3 into z power minus 3. H of minus z equal to h of 0 minus h of 1 into z power minus 1 plus h of 2 into z power minus 2 minus h of 3 into z power minus 3. H of minus z power minus 1 equal to h of 0 minus h of 1 into z plus h of 2 into z square minus h of 3 into z cube. Minus z cube into h of minus z power minus 1 equal to minus h of 0 into z power minus 3 plus h of 1 into z power minus 2 minus h of 2 into z power minus 1 plus h of 3 equal to h of 3 minus h of 2 into z power minus 1 plus h of 1 into z power minus 2 minus h of 0 into z power minus 3. Thus, the impulse response of h1 of z is given by h1 of n equal to minus nh of m minus n for 0 less than or equal to n less than or equal to m. The impulse response and the frequency response of the filters used in a perfect reconstruction bank are given by h naught of n equal to h of n under dtft gives h naught of e power j omega equal to h of e power j omega. h1 of n equal to minus 1 the whole power n into h of m minus n. Under dtft it gives h naught of e power j omega equal to minus h of e power minus j omega into e power minus j omega m. G naught of n equal to h of m minus n. Under dtft it gives g naught of e power j omega equal to 2 times of h of e power minus j omega into e power minus j omega m. G1 of n equal to minus of minus 1 the whole power n h of n. Under dtft it gives g1 of e power j omega equal to minus 2 h of e power minus j omega. The design procedure of a perfect reconstruction of CQF bank as the following steps. Number 1. Design a low pass zero phase off band FIR filter or not offset of order 2m where the number m must be an odd integer. Number 2. If the minimum value delta minimum of the real and even function or not of e power j omega is negative, form a non-negative function as r plus of e power j omega equal to r naught of e power j omega plus modulus of delta minimum greater than or equal to 0 is called equation number 10.1.101. This is equivalent to adding the value modulus of delta minimum to the sample r naught of 0, that is r plus of n equal to r naught of n plus modulus of delta minimum into delta of n is called equation number 10.1.102. Number 3. Scale r plus of z so that the frequency response is equal to 1 by 2 at omega equal to pi by 2. R of z equal to 1 by 2 divided by 1 by 2 plus modulus of delta minimum into r plus of z is called equation number 10.1.103. Number 4. Determine the minimum phase filter h of z by solving the spectral factorization problem r of z equal to h of z into h of z power minus 1. Number 5. Specify the remaining filters of the bank. FIR quadrature mirror filter QMF banks. Quadrature mirror filter QMF banks provide complete cancellation of the output aliasing error, but the perfect reconstruction property is only approximately satisfied. The basic idea is to design a low pass filter h of z and then determine the filters in the bank as follows. H naught of z equal to h of z, h1 of z equal to h of minus z is called equation number 10.1.104a. G naught of z equal to h of z, g1 of z equal to minus h of minus z is called equation number 10.1.104b. The time and frequency domain characteristics of these filters are given by h naught of n equal to h of n under dtft h naught of e power j omega equal to h of e power j omega, h1 of n equal to minus 1 whole power n h of n under dtft h1 of e power j omega equal to h of e power j of omega minus pi, g naught of n equal to h of n under dtft g naught of e power j omega equal to h of e power j omega, g1 of n equal to minus 1 whole power n plus 1 h of n under dtft h1 of e power j omega equal to minus h of e power j of omega minus pi, where clearly h of e power j of omega minus pi is high pass filter. A simple change of variables yields modulus of h1 of e power j of pi by 2 minus omega equal to modulus of h naught of e power j of pi by 2 plus omega is called equation number 10.1.105. That is, the magnitude responses are symmetric about the quadrature frequency omega equal to 2 pi by 4. The symmetry led to the term quadrature mirror filter banks. Using the following polyphase decomposition of the low pass prototype, h of z equal to p naught of z square plus z power minus 1 into p1 of z square is called equation number 10.1.106. We can obtain the efficient implementation of the QMF bank. To determine the properties of QMF banks, we compute the quantities A of z, T of z and delta m of z. The QMF bank is aliasing free because A of z equal to h naught of minus z into g naught of z plus h1 of minus z into g1 of z equal to h of minus z into h of z minus h of z into h of minus z equal to 0 is called equation number 10.1.107. The system function of the alias free QMF bank is given by T of z equal to h naught of z into g naught of z plus h1 of z into g1 of z equal to h square of z minus h square of minus z is called equation number 10.1.108. Finally, the determinant is given by delta m of z equal to h naught of z into h1 of minus z minus h naught of minus z into h1 of z equal to h square of z minus h square of minus z is called equation number 10.1.109. From 10.1.106, 10.1.108 and 10.1.109, we obtain T of z equal to delta m of z equal to 2 into z power minus 1 into p naught of z square into p1 of z square is called equation number 10.1.110. If the product p naught of z square, p1 of z square is a purely delay conditions 10.1.107 and 10.1.110 ensure that perfect reconstruction with an FIR filter bank is possible. To satisfy this requirement, we choose p naught of z equal to b naught into z power minus n naught and p1 of z equal to b1 into z power minus n1. Then the filter h of z as the form h of z equal to b naught into z power minus 2n naught plus b1 into z power minus 2n1 plus 1 is called equation number 10.1.111, which is of limited practical usefulness. In conclusion, there are no practical alias free FIR QMF banks with perfect reconstruction. Polyphase implementation of the two-channel QMF filter bank. Elimination of phase distortion. If we restrict h of z to be an FIR filter with linear phase, then T of z also has linear phase. Thus, we can create an alias-free QMF bank without phase distortion. A low-pass FIR filter with linear phase should have a symmetric impulse response type 1 or 2, and its frequency response can be expressed as h of e power j omega equal to a of e power j omega into e power minus j omega m by 2 is called equation number 10.1.112. Substituting 10.1.112 into 10.1.108 and recalling that modulus of h of e power j omega as even symmetry, we obtain T of e power j omega equal to e power minus j omega m within the bracket modulus of h of e power j omega the whole square minus 1 the whole power m modulus of h of e power j of omega minus pi the whole square is called equation number 10.1.113. If m is even, then T of e power j pi by 2 equal to 0, which causes severe amplitude distortion in the signal transmission path. Therefore, we must choose m to be an odd number type 2 FIR filter, which leads to the following relation: T of e power j omega equal to e power minus j omega m within the bracket modulus of h of e power j omega the whole square plus modulus of h of e power j of omega minus pi the whole square is called equation number 10.1.114a equal to e power minus j omega m within the bracket modulus of h of e power j omega the whole square plus modulus of h1 of e power j omega the whole square is called equation number 10.1.114b. Perfect reconstruction requires h0 of z and h1 of z to be power complementary, that is modulus of h0 of e power j omega the whole square plus modulus of h1 of e power j omega the whole square equal to 1 is called equation number 10.1.115. However, the only FIR filter satisfying 10.1.115 are the trivial filters in 10.1.111. Thus, it is not possible to design practical FIR QMF banks with perfect reconstruction. Johnston, 1980, proposed a design technique based on minimization of the following criterion: j equal to alpha into integral omega s to pi modulus of h of e power j omega the whole square into d omega plus 1 minus alpha into integral 0 to pi within the bracket 1 minus modulus of t into e power j omega the whole square into d omega is called equation number 10.1.116, where alpha is a weighting factor in the range 0 less than alpha less than 1. Impulse response, magnitude responses and a magnitude distortion function for a QMF bank designed using the linear phase Johnston 16B filter. Multi-channel filter banks. The matrix approach can be extended and used to obtain closed form solutions for designing K-channel filters banks without aliasing and with perfect reconstruction. However, the design process is complicated because we have to find K different filters that satisfy the conditions for perfect reconstruction. In this section, we discuss two simple approaches to bypass this problem. In the first approach, all required filters are derived from a single low-pass prototype using modulation. In the second approach, we use a two-channel filter bank in a tree structure. Modulated filter banks. The basic idea is to start with a low-pass prototype filter and create all other filters by frequency translation. Consider a prototype causal low-pass filter h of z with a real impulse response h of n and approximate bandwidth pi by k. The analysis filter are defined by hk of n equal to h of n into e power j of 2 pi by k into kn equal to h of n into wk power minus kn, where k equal to 0, 1, etc. up to k minus 1 is called equation number 10.1.117. where wk approximately equal to e power minus j 2 pi by k is the twiddle factor. The z transform of 10.1.117 is given by hk of z equal to summation n equal to 0 infinity hk of n into z power minus n equal to summation n equal to 0 to infinity h of n into z into wk power k the whole power minus n equal to h of z into wk power k is called equation number 10.1.118. Evaluating the z transform for z equal to e power j omega yields the frequency response functions hk of e power j omega equal to h of e power j of omega minus 2 pi by k, where k equal to 0, 1, etc. up to k minus 1 is called equation number 10.1.119. The filter bank obtained in computationally inefficient. However, we can obtain a more efficient implementation using the polyphase decomposition of the prototype filter given by h of z equal to summation m equal to 0 to k minus 1 z power minus m into pm of z power k is called equation number 10.1.120, where pm of z equal to summation n equal to 0 to infinity pk of nk plus m into z power minus n is called equation number 10.1.121. Replacing z by z into wk power w in 10.1.120 and using the identity wk power kk equal to 1, we obtain k-band polyphase decomposition of hk of z. The result is hk of z equal to summation m equal to 0 to k minus 1 z power minus m into wk power minus km pm of z power k into wk power kk equal to summation m equal to 0 to k minus 1 z power minus m into wk power minus km pm of z power k. This is a set of k linear equations which can be written in matrix form as follows. Is called equation number 10.1.122. the above matrix is equal to the conjugate of the k-point DFT matrix, that is Wk equal to n into Wk power minus 1. Thus, the matrix by vector multiplication in 10.1.122 computes the inverse DFT of the polyphase vector multiplied by n. The filter bank obtained is known as a uniform DFT filter bank. The computational complexity of a polyphase bank using FIR filter with n coefficients is n by k plus 2 log 2k plus 1 real multipliers per input sample compared to 2kn real multipliers for the original bank. Perfect reconstruction with IIR filters is possible. However, either the analysis or synthesis filters are non-causal and performance may be poor. A widely used approach is to design consecutive pairs of filters that are approximately power complementary between their center frequencies. All other alias spectra are suppressed by designing a prototype filter with sufficiently high stop band attenuation. Such filter banks are known as pseudo QMF banks. If the modulation by complex exponentials is replaced by cosine modulation, we obtain cosine modulated filter banks. First step towards a polyphase uniform DFT analysis filter bank. A, B polyphase implementation of a uniform DFT filter bank. Tree structured filter banks. An alternative way to split a signal into multiple subbands is by using tree structured filter banks. A simple way to design the required filters is by cascading two channel filter banks. The most widely used structures are A, the uniform band tree structure, B, the octave band tree structure. If the two band filter banks used as building blocks a perfect tree construction, the resulting tree structured band provides perfect tree construction as well. The uniform band tree structure is essentially a different implementation of a uniform filter bank with k equal to 2k channels. The octave band tree structure provides a non-uniform logarithmic decomposition of the spectrum, which is useful in many coding applications. The original signal is split into two equal frequency bands by a low pass off band filter H0 of Z and a high pass off band filter H1 of Z. The upper channel produces a low frequency smooth signal and the lower channel produces a high frequency detailed signal. The octave tree bank provides a multi-resolution decomposition of the original signal, since multi-resolution decomposition are closely related to the discrete wavelet transform. Basically, the discrete wavelet transform is an octave tree filter bank with analysis and synthesis filters that satisfy some special properties. Conclusion. In this chapter, the user would learn the following in detail: multi-rate signal processing, adaptive signal processing, finite word length effect.